And I begin with a short presentation to find that people join. To be okay. So welcome, my name is Florent Echtel. The surgery here. So together with Guillaume Fogeda and Alexandre Arnold, our colleagues who have prepared also the tutorial that they could not have this year. We are from Airbus Research, so meaning working on different programs for aircraft, satellite mission planning, helicopters, or any kind of problem for vehicles that fly, for which there is a need for research. And so we developed this library, scikit-decide, together with other projects, so the INITI Artificial Intelligence Institute in Toulouse, and the TOEFL's project, European Union project on trustworthy artificial intelligence, which is led by CVKB. So this is the agenda for today, and it's quite flexible. It's just a proposition. We can adapt depending on how long it will take to run the notebooks and to give explanations and so on. So we will begin with a presentation of the general concepts of the library, and then we will go through the notebooks that you will be able to open in Colab or on your computer if you prefer. So the first part will be on solving domains. So domains are problems or environments like in reinforcement learning with auto-selected compatible solvers. So you will see that this library offers a way, once you define a domain, to propose you a set of solvers that can tackle this domain. With 3 notebooks, the first one on solving control problems like the card pole or the mountain car with reinforcement learning and genetic programming solvers. The second one on solving scheduling problems, which are of a totally different nature, with constraint programming, operation research, and also a link to reinforcement learning. We will see how it's possible. And finally, a third notebook on solving PDDL problems, so with classical planning, obviously, but also with reinforcement learning solvers. And you will see that with the library, just changing from classical planning to reinforcement learning, it's just changing one line of code in the notebook. Okay, once we've seen that, the second part will learn you how to implement your own domains and solvers, which is an interesting part. So as practitioners in the industry, we are interested in modeling domains and then solving them automatically with solvers. And in academia, it's rather the opposite. So we give you domains and then you're interested in implementing solvers to solve those domains. So there will be 2 notebooks. So number 4 on implementing a scikit-decide domain for riddle problems. Riddle is relational domain definition language, which is a probabilistic language for planning. And the 5th notebook about implementing a scikit-decide solver, which embeds some riddle solvers that will be presented, by the way, this Thursday in ICAPS. Those solvers are not by us, but they are already available on GitHub, and so we have embedded them in scikit-decide. So Jackson and you will be on. And so we'll conclude with some guidelines, some applications on our side in Airbus, and future developments. Okay? All right, so introduction to the library. So scikit-decide is an AI toolbox to do 3 things: reinforcement planning, automated planning, and scheduling. So it's really the objective of having in one library a set of things that can solve sequential decision-making problems. It was initiated by Airbus at the beginning, but developed strongly in a research project, AI Plan for EU, for which there was a tutorial last year in ICAPS. So AI Plan for EU focuses really on PDDL planning. And it helps us a lot developing the PDDL part of the library, actually, and the TOEFL's European Union project. It was also developed with a lot of support and expertise by ANU, so Australian National University, which contributed to some of the algorithms in the library. So the primary focus for us, coming from the industry, was on problem solving. Okay? Meaning that we wanted a library where there is no need for the end user, typically an engineer, to be an expert of decision making, to be able to model a domain and solve it. It offers an extensible architecture with domain and algorithm catalog. We'll see this in a minute. And importantly, it's open source. So anyone can contribute look at the code, make pull requests, report bugs, and everything. And so you have the link here to the library on GitHub. So we'll come back to this process, but it's quite important. It's really the spirit of the library. So in order for an end user to be able to easily define a domain, we thought that we would focus the library on capabilities of the domains. So as an end user, you know if, for instance, you have exogenous events like Eclipse, or if all the events are controlled, so your interactions in that case, or if there are unrestricted actions, meaning that all the actions are applicable in any state, like it's common in reinforcement learning, for instance. For the dynamics, you could have access just to a reinforcement learning environment with a step function, or a simulation, meaning that you can start from any state, and so on. Okay, so typically, when you define your domain, and we'll see this in one of the latest notebooks, you define those characteristics, and then you have a few methods to implement, so that the solvers then can request those methods. That's the spirit. In terms of research ecosystem, I already mentioned it. So we have Orpheum National University, AI Plan for EU, whose ambition is to bring AI to the European on-demand AI platform. And so we provided bridges to scikit-decide and Reversely. And Tuples, on the other side, is a library focusing on trustworthy decision-making techniques, led by CVTable, as I said. And all the algorithms developed in Tuples, including explainable algorithms, computing, for instance, minimum and satisfiable subsets, or their counterpart mugs in planning, will be included in scikit-decide eventually, so within 1 year. And by the way, we will organize a competition in Tuples. You will have some advertisement this week in ICAPS, and so there will be nice prices, and the competition will be run within the scikit-decide framework, in fact. And why? Because it will allow us to grab people from reinforcement learning, from planning, from scheduling, from different areas, because with one problem formulation, we can address different communities, and that's the objective.
Where are you going to advertise this?
So in 2 workshops. So today at the same time, unfortunately, in the IPC workshop, and tomorrow the explainable planning workshop. And I have some competition postcards here, by the way, so I can give you them later. So the library is split in 2 different things. Domains on one part, where we have a bunch of academic domains, binding to existing domain libraries like OpenIGM, Unified Planning. Also some, let's say, realistic domains from Airbus. They are representative of the real domain, because the real ones are confidential, but very close, like flight planning, which are so freely available in the library if you want to test your algorithm on those domains. And then we have solvers of different kinds, right? So search algorithms like A*, iterated grids, MCTS and its variants, LRTDP, LR*, many such algorithms. Then reinforcement learning, mainly via bridges to RLU and stable baselines, because those are state-of-the-art libraries, so we don't want to reinvent the wheel just to make the bridges. Then we have scheduling and routing via another library, discrete optimization, which itself links to CPSAT, to Ruby, to many kinds of different frameworks. But you don't see, everything is done under the hood by the library. And PDDL planning. And so you see, we separate clearly the problems of domains and solvers. There is this dash line where the magic basically is done, but we will see how in the library. Yeah, one important thing. So the library provides a hub. So a hub is a kind of set or library of solvers and domains which are available here. But you can extend it easily with your own solvers and domains. That can be fine-tuned, that can be internal and confidential, that can be demonstrations, and so on. So it's really play and play. So we have default solvers and domains, and you can add more if you want. In terms of solvers, we have those 3 things. I think, yeah, I already spoke about it, so no need to spend more time on this slide. So we respect open source standards. What does it mean? So first, you can easily install the library. There are two kinds of installs. The Python one, which is quite easy. You can install it via PyPy. Just pip install scikit-decide. But we have also the C++ library. It's a bit more advanced. You need to compile the things with CMake and so on. So I would say that the end user wouldn't use the C++ part. But as a solver developer, it's important because most algorithms in the library are developed in C++, and then you just make the envelope with Python. It has an extensive documentation. We could read in a minute. Many examples, an online. We already have an online tutorial, which is different from the ICAPS one, which is on the website also. Some code generators. We'll speak about it in the two last books. Unit and integration test. It means that whenever you make a pull request, all the unit tests are running. You have to provide unit tests, otherwise we don't accept the pull request. It's run every night, and when the test passes, so every night you have a new release of the library. Okay, so now domain features and solver capabilities. How do we make the links? You know, this dash line between domains and solvers. So here you see an excerpt, okay, of the different domain features. We have observability, whether the domain is partially observable or fully observable. Memory, depending on whether you need the full history of state action, from the initial state to the current one. The history is finite. It's Markovian, depending only on the last state, or memoryless. If I'm rolling a dice, okay, would be a memoryless domain. The horizon can be infinite, finite. Initialization, whether the domain is initializable from a given initial state, or if the initial state can be randomly initialized, or if it is deterministic, like in planning. Value can be reward or cost. It's quite obvious. Events, whether you have exogenous events or if everything is controlled in actions. And finally, the dynamics, so from environment, like in Gym, to really the white box model, where you define the state transition functions. And even in a probabilistic domain, you would define the state probability transition function. Okay, so now imagine that you define a domain with those characteristics. So you're reasoning about cost, your initial state is uncertain, initialized with some uncertainty, horizon is infinite, memory is Markovian, and so on. Now you will define a solver with those capabilities. So the envelope of the solver is larger. What does it mean? It means that if the solver, for instance, can handle the, let's say, partial observability, obviously it can also handle fully observable domains. So that's the principle. You define a solver with a given envelope, and it can solve all the domains which are in the enclosed envelope. So meaning it can also solve the blue domain, but all the ones, okay, which are included in the yellow one.
But maybe that's stupid to ask questions as well.
Yeah, for sure.
But maybe that would mean that that's not the best solver for that.
Yes. You're pretty right. So the more generic the solver, the less efficient it is on a specific domain. But sometimes we can have some surprises. And so you can ask for instance, you can make a script that compare all the solvers which are compatible with a given domain and see which one works well. But you're right, yeah. And that's the principle. When you define the domain, then the library will check all the solvers which contain it. Now, another interesting stuff is the management of parallel domains. It's something which is done in RLE and stable baseline. So in reinforcement learning, it's common to parallelize the domain and to solve many domains in parallel using multiprocessing. So we've done the same here, and it's totally hidden by the end user. So the end user defines the domain once, and then the library will automatically generate parallel processes of two different kinds, either by using pipes, which is the easier way to do it, but not that efficient, and more advanced ones with shared memory, but you have to give more insights to the library in order to know how to share the memory of the objects in the domain between the processes. Obviously, that one is much more efficient, but it requires a bit more input from the user. And then it means that under the hood, okay, the solver will parallelize so either the rollouts in NCTS algorithms or the generation of next states, for instance, in star search. And you may wonder why, because when you know the model, for instance, of the domain, parallelizing the generation of the next state does not make sense. But in fact, in the industry, most of the time, we rely on a simulator to generate the next state, and this simulator can be very long to compute the next states. And then it is useful to parallelize the generation of the next state, and we can gain a lot of time. So that one is an important one. The bridges between AI plan for AU, which is about PDDL planning, and scikit-decide. Because thanks to this bridge, we can, on one side, solve PDDL problem with scikit-decide, but also from the other side, so solve PDDL problems using. Sorry, I mixed myself. So on one side, we can solve PDDL problem using unified planning from AI plan for you in scikit-decide. But reversely, in unified planning, they can use scikit-decide solvers to solve problems where there are extended things in PDDL, like for instance, having a function which simulates some battery discharge, which is something that you cannot do easily in PDDL, and that scikit-decide can handle naturally. And so they also have some kind of bridge to scikit-decide, and we will use it actually. Okay, now what is the structure of the library? So if you go to the website of the library, on your computer, you can do it here. I can show you. So this is the GitHub website of the library. If you enter just github.com/erber/scikit-decide. Okay, you follow on this web page. And you also have a link to the online documentation here. Okay. Now, on the slides, I just extracted the structure of the library. So you can navigate it in GitHub. So, first of all, what we're on the top is Binder, which is a notebook environment. I don't know if you know Binder, which is more efficient than Colab. And so every night we build Binder environments, so you can also launch notebooks on Binder, which is more efficient than Colab. Okay. But only for the notebooks which are part of the official documentation, not the ones of the ICAPS tutorial. We have the folder CPP, which contains all the CPP API and the algorithms. But today in the tutorial, we will just focus on Python. So all the examples are in the folder. Examples, all the notebooks folder. Then we have all the unit tests here in the test folder, and some utils here. So the important part, so when it's like this directory, scikit-decide, when you install the library with PyPy, in fact, you get all the things inside this folder. So it contains builders and the hub, which are different things. So the builders are, in fact, the core functions of the library from which you can build new domains and new solvers. So for instance, for the domain here, we recognize all the features that were part of the ROSAS. And each of them are part of a different Python script. I didn't show you, but we also have the same ROSAS for the solvers. So solvers can be accessible. Like you can request, for instance, the value of a plan in a given state. You can solve it from a given state or from just the initial state of the environment. You can parallelize it. It is based on policy. You can restore the solution or not. This is for the builders. And then the hub, which are some build blocks that we already offer, as I said. And we have three kinds of blocks: the domain, the solver, and the spaces also. So for the domain, what do we have? We have flight planning, gym domains, which is a bridge to OpenAI gym environments.
Gym, not gymnasium.
Gymnasium now, actually. Yeah, we didn't change the name, it is gymnasium. And then some, let's say, toy problems that allow us to understand how the library works. So mastermind, for which we show how to solve. It's a POMDP problem that we solve with POMCP. Then the maze, RCPSP, so which stands for Resource Constraint Project Scheduling Problem. So it's a scheduling problem. Rock, paper, scissors, the famous one, which is a multi-agent domain. Griswold, NUP for unified planning. So solvers, I won't enumerate all of them, the list is too long. But it means that all the solvers are brought in addition to the bridges to stable baselines, which is here, unified planning, and where is RLib here. But apart from those three, all the other ones are implemented directly within the library.
Yeah. So if I'm right, builders is made for creating new solvers and domains, and
Yes.
HUD just integrates already known
Exactly.
domains and solvers.
Yes.
Okay.
And you are free to extend this list. We do it as the project goes, as new problems arrive. And so the objective, as an open source library, is that the community will extend it, of course. Okay, now it's time to go to the tutorial. So please go to this page. Normally you have the link in the ICAPS webpage itself. So you click on tutorial, on the tutorial scikit-decide, and then it will bring you to this site. So normally you arrive here. Okay. Then you click on notebooks. And so for each notebook, we provide three kinds of links. Open in Collab, which is what I recommend for today. And seeing the tutorial on GitHub, not very useful today. And the HTML version, so which is an HTML extract, okay, of the notebooks that we have run on our site. So just in case there are issues during the tutorial, we'll go to the HTML page to see the results. Some algorithms can be a bit long to converge, by the way, like a reinforcement learning solver. So maybe we'll see, but if it's too long, we'll go to the HTML page. Okay, let's start with the first one. So solving control problems with reinforcement learning and genetic programming. Okay, so the first thing to do is to install scikit-decide. So let's click on it.
We launched the notebook one in Collab, right?
Yes, in Collab. Okay. If you want, you can also install the library on your computer. It's before you need to install Python environment. Yeah, so it retrieves a lot of things, as you see. That library is important for studying problems with Gymnasium, double baselines. Normally it takes 2 minutes maximum. Okay, then we will use that one, render lab. So it's render lab is just an environment on top of Gymnasium that allows us to record movies. Okay.
Should we enable GPU to make things faster?
You can, but that said, in this tutorial we will solve very simple problems like the car code. Won't make a big difference, but yeah, why not?
So the library have the ability to utilize GPU.
Oh, yeah, well, in fact, the library relies on solvers like stable baselines and IRLib. So in fact, you will have GPU if you install those libraries with GPU. You could install it on your site. It's already done. Okay. So if you want, you can save time by opening the other notebooks and already running the first cell. I think we can open up to 2 or 3 notebooks.
You think it will be relevant to start now? It was not,
Yeah. So I've for instance, here I've opened the second one, and I think we can already here install stuff. So we'll save time. Okay, now it should be finished on the other side. Not yet. Okay. Okay, now it should be 2 minutes only. Okay, strange. Okay, now it's done on my side. I don't know why I had to restart the notebook and rerun the first step. Now it's working. You too? Yeah, I don't know why. Okay, now we install RenderLab. Okay. So, yeah, once the program is formalized in scikit-decide, you can tackle it by any compatible solver. And you can either create domain from scratch or import them from existing ones. So here we will import the cartpole domain from Gymnasium. So everyone knows Gymnasium here? Approximately. Okay. Yeah, so it's a framework for reinforcement learning, which defines, in fact, domains in a standard format. But then other reinforcement learning libraries like Stable Design and RLib can use to solve a lot of benchmarks, well-known benchmarks from the RL community. Cartpole is one of them. You have a rendering, and so basically it's a cartpole that you must control. It's moving, so you have to control its movement so it stays like this, like it stands and it's not falling. Okay, what do we do? First, we import Gymnasium. I don't know how to say it. Gymnasium. Okay. But by the way, sorry for my accent. If you don't understand me, just interrupt me and ask me again.
I get it.
Okay. Okay, RenderLab is just something on top of Gymnasium, so to record movie. And then we import the gym bridge from scikit-decide, from the hub. Okay, scikit-decide.hub.domain.gym, import gym domain. So the first part is very common to all Gymnasium domain loading. So you define the env name. And then we define what we call the domain factory, which is a lambda function that will create a domain. And why is it a lambda function? Because remember, I told you about parallel domains. And so those parallel domains are created in separate processes. And this is why we need to provide to the solvers a way to build those domains and not to give them instances. This is why we always provide domain with lambda functions. So here, this is a function. Why? Because we are adding, in fact, this movie recording capability to the notebook. But normally, in real life, okay, you will just define the lambda function in one line, like the one here.
Then it won't render?
If you do that, you won't render. So not in the normal. You won't create a movie, and in Colab it's a bit cumbersome. So this is why, to make it work with Colab, we prefer building them. But if you do that in a normal Python script, it will still render. In a separate Python window, in fact, and not inside the notebook. Okay, so that one is easy. It's just defining a function. It does not run anything. Okay, now we will roll out a random domain. Sorry, a random solver. Not yet the reinforcement learning solver. So to do this, we first create our domain here, and then we will roll out it. So rollouting a solution is calling a solver and asking it for the next action in each step. And so the rollout function is provided by scikit-decide in the utils. Okay, so you can find it from scikit-decide.utils import rollout. You can define the number of steps, the number of episodes, whether you want it to be verbose or not. I recommend to put verbose equal false unless you want to debug your domain. So last, yeah?
Where did you set the solver?
So here we don't set a solver, it will be just random walk.
But
When you
where
don't
did
set a solver.
So the rollout was, rollout is always random?
No, it depends. So in fact, if you give a solver to the rollout function, and we will see it just after, then it will use a solver.
But
If you,
otherwise it's random.
yeah, exactly. Actually, we can see it here. If I'm asking for the, I should create it before then. Yeah, so here the signature of the rollout function. You see here, we have the solver, and if it's none, then it will be a random walk.
But it can't accept the policy.
No, it accepts a solver that can itself load the policy. And actually, the solver that we will use here will do that. And then you can give a starting state from memory, or otherwise it will be the initial state of the environment if there is one, and so on. You have different options. Okay, so here, yeah. So what it has done, so it has just done a random rollout, okay, of the environment, recorded it in some videos, and imported then the video here. So if we play it, yeah, it stops quite quickly because whenever the card pole falls down, then it terminates the episode. And since it's random here, it lasts for a very few steps. You can see it again. Down. Okay, meaning that in the next frame it would fall down. So obviously we want to learn to control it. Okay, so the first one is to use arraylib, and then we'll use table baselines. And also in the reverse order. The first table baselines and then arraylib. So in stable baselines, they provide different reinforcement planning solver. That's not the pick today to go through them. We'll use just one of them, which is well known, which is PPO, proximal policy optimization. So which is a policy optimization algorithms where the algorithm will learn to optimize, in fact, the action distribution of the policy when interacting with the environment. It's a bit more complex than that, because there are many different policy optimization algorithms in reinforcement planning. So PPO is one of the most famous ones. Okay, then we import the stable baseline bridge with this line here. We check that stable baseline is compatible with our domain, meaning that the envelope of the solver is larger than the one of the domain. It's what's done in this line here. And then here we call the solver. So we give it the domain factory, the lambda function that will create the solver. Then the other parameters will depend on the solver. But for the stable baseline solver, we give it the algorithm class from stable baselines. We define the type of policy. Here is simply a classical deep network, fully connected deep network, MLP policy, and then the learning config. So we will ask it to do only 10,000 optimization steps, but it should be sufficient for the card pole, which is a very simple control problem. Once you've created the solver, you call solver.solve, and then we can save, in fact, the policy. And it relates to your question. So here we will save what has been learned so far in the, folder name saved solution. So let's do that. Okay. So the deprecation warning are not on our side, unfortunately. You will see that with the RLlib there are even more. So we hope that we'll fix it before we cannot run them anymore. Okay, so it's learning something. So the loss is increasing at the moment. But yeah. Okay, what has it learned? So this time we will roll out the solution and we will give it the solver. That's the difference. And by doing so, it will ask the solver of the next action. So how does it do it? Let's have a look at the solver class. Yeah. So it was here. I'm making a quick digression. So if I go to the builders here, solver, okay. Okay. So the stable baseline solver re-implements this abstract class policies. So in fact, in this policy, we define the sample action methods, which in fact all that one. That has to be re-implemented by each solver. We'll see it in the end. You see it's not implemented. And so it's re-implemented typically by stable baseline. And so the rollout function will call the sample action on each state. And this will allow us, right, to visualize the solution. So it's very quick. Everything has been recorded in this MP4 video. And if we play it here, we see that, okay, this one was quite bad. And we could see the loss actually increasing. If you paid attention, the loss increased, meaning that it has not learned much. So what we'll try to do now is to continue optimizing the policy. So we load the saved solution. We call solve again to continue optimizing it, and we will resave it just in case.
So this allows you also to monitor the performance of the algorithm per iteration.
Exactly, yeah. Okay, let's see. Okay, no, it's fine. You can control the card pool. Deal. No, but it's better, okay, than the previous one. Also, it's a bit stochastic, so if you rerun it a second time, maybe it will be different. So some solvers have to be cleaned. For instance, when you run parallel domains, you want to close all the processes, all the pipes. So you have to close the domain and the solver. So either you do it with this line of code, or you call the solver within a with statement, and we'll do it later. We will always call the solver within a with statement that will automatically close everything. Okay, let's try another solver. That's the interesting part of scikit-decide. So people in reinforcement learning, they would typically use, with this kind of domain, the solvers from their community, meaning the PPO, DQN, AQC, all these kinds of solvers from reinforcement learning. But in fact, we can use much more solvers. Something that is not in the notebook here, but that I can show, is to get the list of compatible solvers, actually. And it's done by this line of code. Yeah. And so if I print match solvers of our domain, I think it's like that. We'll see. Domain or domain factory? I think it's domain. We'll see. Yes.
Scroll up a bit.
Yeah, it's that one. I'd like to have a more a better view of this.
This gives the solver solvers that are.
Yeah, that are compatible. So yeah, so we see we have augmented random search. We have CGP, that one that we will are going to use now. MAD, it's a multi-agent solver. Sorry, it's okay. So MAD is a multi-agent solver. So obviously, you will not use it for this domain, but a multi-agent solver can handle a single agent domain. But definitely, we're not gonna recommend doing this. We have inverse reinforcement learning. Okay, sorry. RLlib and stable baselines. So it means that we can go beyond the traditional reinforcement learning algorithms. And so we try something from genetic programming, a community which is totally different, which publishes in Gecko, for instance, not in RIPS, typically. And so CGP is a control algorithm that we try to learn, not a deep network, but in fact, an approximation function as a tree of operators. So we will define the operators you want to see in the tree, like plus, minus, divide, cosine, sinus, etc. You can imagine every kind of operator. So we give the set of operators that are allowed, and then the algorithm will try to learn and approximate policy function and value function with those operators. And so, really, to call it in scikit-decide, it's not more difficult than calling the reinforcement learning solver that we had here. So first we check that CGP is compatible with our domain. We already know that it is, because with the match solver call that I done just before, it appears in the list. So obviously it is compatible. And here it's a call with a with statement, as I told you. So we say, with CGP, we give it a domain factory. So this algorithm needs a temporary folder to make its computation and a given number of iterations. We say, okay, with this algorithm as our solver, we call the solver and then we do some rollout. Okay, let's do this. And so we can see in this domain, it does not perform well. So you can say, okay, this algorithm from this other community for this domain is not very good. But hold on. Later, we will see the mountain car domain from reinforcement learning, which is more difficult to solve by, for instance, the RLlib and stable baseline, and which is astonishingly very easy to solve with CGP. We will see that CGP can solve it very well.
I'm not sure to understand the thing. When you do your reinforcement learning with your algorithm, the number of iterations is already included in the function.
Yes.
Right. So but here you did like 50 iterations, and before it was
With which one? With
the last one, this one.
here.
Yeah.
Okay.
Before it was like I don't know.
10,000. In fact, the parameters here are specific to the algorithm. And so, depending on the algorithm, they can have different meanings.
But can you compare like 50 iteration of this algorithm with the previous algorithm, which was working differently?
No, not really. You have to play with the parameters.
Okay, so here it's just arbitrary to say that this one is not performing as well as the others.
Yeah.
Okay.
Very good question. We'll see that for the scheduling API, we have a way to optimize the parameters. It is still not ported to the whole library. It's ongoing work. And so we will be able in a few months to compare different algorithms along with their different parameters.
Okay.
And we will see in scheduling how it works. It's using the Optima framework. It's quite easy to do it that way. That's why you can increase it. Honestly, for this domain, CGP is not working well. So even if you increase the number of iterations, you won't get much better results.
You know this because you have experience.
Yes.
Okay.
Because when we worked on the tutorial, we tried different things. And so we know that here it's not working well. We'll see in another other book, we know the current stuff.
Okay.
It's also a benefit of the library, so you can try different algorithms. Sometimes you have good surprises that were not expected depending on the domain. Okay. Yeah. So normally what we would show here is an algorithm typical from ICAPS in the search community, which is rollout IW, iterated width. It's part of the library. Unfortunately, they recently changed some parts of the gymnasium library, and so from recent weeks, rollout IW is not able to work well with this domain, so we won't show you. We are working on it, but normally it's also working okay, even well. There are papers from the ICAPS community showing that you can use width algorithms to solve control problems. It's part of the scikit-decide, but yeah, unfortunately, due to those very recent changes, I can't show you them today.
What changes?
In Gymnasium, so they for instance, they added a boolean in the step function. Now there are two different things. Either you can before they return it a boolean indicating if the episode terminates or not.
Is that?
And now they added the second one, which is truncated. It means that the episode ended, but it's truncated. And it changes a lot of things.
The API change.
The API change,
Okay.
the meaning of the rollouts also. And so we are adapting it. So rollout IW can again work well with this.
So specifically, there is a specific algorithm that was affected by this? Rollout.
All the algorithms are affected. The reinforcement learning algorithms that are brought to us by stable baselines are already adapted, so this is why they are working.
Okay.
And the ones from our library, which are specific to our library, needs to be adapted.
I see.
Yeah, maybe I can show you. We'll see it working. The thing is that it does not understand the truncated thing. Where is it? I can show you, and just to show you that it's possible to call search algorithms.
Because the search algorithms are part of your library.
Yeah. So this is the same notebook here, opened in Jupyter Lab on my installation of scikit-decide. And so yeah, here this is a rollout IW part. So IW means iterated width. So it's an algorithm that computes the width of a domain somehow, which depends on, it's a bit difficult to explain. But typically the width of the domain is based on computing the different subsets of variables in a domain. And a domain would have a width of 1, for instance, if you can solve the domain by discovering a given variable for the first time. Width of 2, if you need reasonable pairs of variables that you will discover for the first time, and it's sufficient with the one and so on. You can do the same thing with control problems, considering that your variables, for instance, are intervals of continuous. Indeed, that's working very well if you do this. Okay, normally. The only thing that we need to do in the library is to adapt the gene domain to width solvers. So we define a new domain here, which is based on builder blocks that we already provide. So 3 builder blocks. Maybe it's a bit small. Let me try to do. The first block is gym planning domain, which casts the gym domain to a planning domain. Then we need to discretize the actions, because otherwise they are continuous. And finally, to compute also the features of the domain for the width planning, gym domains. So once you've done this, you can just copy paste this template here. Normally, you are able to launch width algorithms. Okay. Well, no big surprise. I told you it won't work here. So it's doing something. So it's working and quickly, but in fact, it's not controlling well the card pool. And also, I don't know why it's not showing here. Okay, well, just to tell you that in fact, with a few adaptations, you can also try search algorithms on control problems in scikit-decide. All right. If there are no questions on this notebook, I propose to go to the scheduling one. Okay, totally different kind of problems. So we are going to a totally different community now. So first thing, what is scheduling and how it is different from planning or control domains? So the characteristics of scheduling problems are totally different. I think most of you already know what it is. And just a reminder, we have parallel tasks, no more sequence of actions. The time dimension is very important. So we need to reason about when to start a task and how long it lasts, okay? You could have complex time-dependent constraints, like you would like to say, my task will begin at most, let's say, 5 time units after having ending the previous one, or just when the previous one ended. Enfin, you can have very different kinds of flexible constraints like that. And also, for most scheduling problems, we already know in advance the tasks that need to be done. The objective is to schedule them, to allocate the starting time of the task. Okay? It's different from planning problem where you don't know in advance the actions that needs to be executed to reach a goal. So it means that the model of such problems is totally different from planning and reinforcement planning. But still, they can have some bridges. We can, for instance, cast a scheduling problem into a planning problem or into a reinforcement planning problem and solve it with reinforcement planning. So the library also offers this. So what are the solving technologies to solve scheduling problems? State-of-the-art technologies are based on constraint programming, simple temporal networks, or also mixed integral linear programming. Clearly not reinforcement planning. But we'll see that now, with reinforcement planning algorithms, we can already challenge the state-of-the-art ones. And we'll see that in the book. So we also developed a scheduling API in scikit-decide, which is a bit different from this ROSAS because, in essence, the scheduling problems are a bit different. And it's a bit complex, so I don't show you the ROSAS here, but just you have to know that we also have the scheduling ROSAS, that we automatically, ROSAS, it's not an English word, ROSAS?
Not that I know. The
Okay,
circles?
this is this picture.
Okay. No, so, yeah.
Rosette.
Rosette?
I don't know.
Rose.
Okay, we call it ROSAS, I thought? Okay, sorry. So it was an English word.
It's fine.
Okay, this structure here. And so we can cast the scheduling structure to the sequential planning structure. So what do we have? A base scheduling domain is single agent. Also, it will not be sequential because tasks are scheduled in parallel. The step function is stateless, but it can be sampled. There is a mistake here. When we cast it also the scheduling domain to a planning problem, we can start from an empty schedule, meaning that it will be deterministic initialized. What would be the actions? It will be to decide when to start the next task. Fully observable, we always know the current status of the schedule. And it can become Markovian if in your state you already know when were all the previous tasks already scheduled and what are the ones which are currently executed. And the goals, it means that all the tasks have been scheduled. So if you want to cast a scheduling problem into a reinforcement planning one, you need to define a domain in the reinforcement planning or sequential plan with those characteristics. Okay, now scheduling problem has additional features if you want to solve it with constraint programming. So we have a reference doc on scheduling features. You can click on the link. And here are all the features that can be defined if you want or redefine for scheduling. So you could have precedence or not. You can have different modes for a task. So what is the task of a mode, for instance? I think we have an example later. But it can be a task can run faster but consumes more resources, for instance. That could. And if there is one single mode, there is only one way to execute the task. You can have variable resource consumption. You can have preemptivity or not. That's very important. So what does preemptivity mean? Imagine a satellite that does some observation on Earth, and when there is an eclipse, it has to stop the current observation and to restart after. So it means that the observation task is preempted for the time of the eclipse. Managing it in scheduling is quite challenging. You can have different resource types or not, different resources units or not, renewable resources or not, and so on. Okay, you have a list here of different features that you would consider to define. Okay, no domain implementation. So behind the wall, as written here, a scikit-decide domain is fully implemented from pure scheduling features, those ones here. But if you want to solve it with, for instance, A-star reinforcement learning, we need to cast it to a planning structure, let's say. And for this, we need to define the state as actions are following. It is done totally under the hood by scikit-decide. You don't do it yourself. We explain it here so you can understand what is done in the hood, but you don't have to do it. So in the state, we have the state of tasks which have already been done, the set of remaining tasks, the set of starting time for each task, current progress, and the resources allocated to each of those tasks, and the resources available. So all of this is encapsulated in the state. And then the actions are the following: deciding when to start a task, and which resources to allocate to this task. Can be also to stop a task or to resume a task if it has been preempted, for instance, and again to allocate some resources to it, or to do nothing. I mean, that's the time progress. Yes?
Does the state also somehow include the mode to the task is scheduled in?
Sorry, the most?
Does the state also include the mode for multi-mode scheduling?
Yes, yes. Yeah, also, yeah. Okay, so let's do it. So we know that it's not the state-of-the-art representation, but what we want to do in the library is to show how we can solve problems from one community using algorithms from another community. To solve scheduling problems. You wouldn't solve scheduling problems by considering it as a sequential decision-making problem.
You wouldn't.
You wouldn't. But you could try. And the library's objective is to build bridges between different communities. Okay, what did you bring back here? Okay, so let's try to solve it with A-star. So there are two different A-star algorithms in the library. The Python one, which is called lazy A-star because it generates the graph on the fly. And there is A-star one, which is in fact implemented in C++, which does the thing, but in C++. Why? Because we started with the Python one, and then found out that it was more efficient with the C++ one, but we kept the Python one for historical reasons. So we define the solver, lazy A-star. The domain factory here consists in just returning the domain that was created normally before. So I guess I've not. Yeah, sorry, I've skipped some cells here, it seems. Yeah, excuse me. Yeah, I thought that I was brought back to the beginning of the notebook, but I was not, in fact. So I skipped all those cells. I'm sorry. So let's execute them.
So here, the RCPSP template is the one that creates that bridge that you mentioned?
Yeah, so first we need to define a scheduling problem and then create the bridge. Sorry to confuse you. I skipped all those cells. So let's come back to the creation of the scheduling problem. So there are many different kinds of scheduling problems. One of them, which is used a lot in the industry, is RCPSP, Resource Constraint Project Scheduling Problem. So RCPSP in short. So it's a well-known scheduling problem, which is an extension of job shop, much more complex, where you have a set of activities M that have precedence constraints, like in job shop. So a given task can be executed only if you executed a set of given tasks before. Okay. On top of those constraints, you have renewable resources. So meaning that you can use them, like using a tool or asking someone to do some task, and then after the task is done, the person can do another task. It's also a renewable resource. But you have a given amount of resource, which is limited. So you have a team of 10 people, you cannot hire more people. This is a limited resource. And at a given time, you cannot exceed this capacity. And you can have different types of resources. And each task would use different kinds of resources. Each activity J takes 3J time minutes to complete. And you can have different goals, but in usual, one usual goal is to minimize emission. The classic variant of RCPSP is multi-mode RCPSP, where each task can be executed in several ways, as I said before. And a very simple example of different modes are either you're in a fast mode, but you consume a lot of resource, or slow mode, which costs less, but it's slow. So let's see what's defined with a single mode RCPSP. So here, yeah, this is what you need to define, in fact, when you want to define the scheduling problems as RCPSP. So it's a single mode, deterministic task transition, deterministic task progression, and so on. So it's an example that shows you that an RCPSP is a particular instantiation of some scheduling features. We offer different classes also. You can define a job shop problem, which is also a different instantiation of those features, and so on. There are plenty in the library. Huh? But then you need to define yeah, sorry, excuse me. Yeah, no, that's it. Yeah. Okay, so now we will implement our very simple RCPSP domain, which inherits from this class here. So let's do this. What do we have here? So the maximum horizon here is 10 in terms of time units. The successors are the following. It means that we have 5 tasks. Task 1 needs task 2 and 4 to have been executed. Task 2 needs task 3 to have been executed. And sorry, it's opposite. I'm a bit tired this morning. The successor of task 1 are tasks 2 and 4. The successor of task 2 is task 3, and so on. It's not the precedence, it's the successor. Yeah.
So like preconditions.
Yeah, exactly. We need also to know the task IDs. So here it's very simple. It's just a set of the IDs. Yes.
If I get it right, 2 needs 1 to be executed.
Yeah, exactly.
Okay.
And 4 needs 1 to be executed. Okay.
Yeah.
The successors of 1 are 2 and 4.
Yeah.
So exactly.
Usually we do the reverse. We define 2 and we ask that 1 is already executed.
Yeah, yeah. In fact, you can define it both ways. And if you define the predecessor of the library, you can get the successors and so on.
Okay.
You have the choice. Yeah. But that's true that in the RCPSP community, I think it's more common to define the predecessor relation than the successor one. But you can do it both ways. So this is why I was confused when I read it. Okay, now the task mode. So we are here using only one mode. And so for each of the tasks here, task 1, 2, 3, 4, 5, we define the mode. So it's a constant mode conception that uses only one resource, the resource 1. And you see here the quantity of resource that it uses. If you would have different resources, it's a dictionary, you would add other keys related to the other resources. We define now the resource types. We only have one resource, type 1, in this very simple problem. And now we define the task durations. Again, it's a dictionary that takes as keys the task IDs and as values the durations.
Is it admitted that when we define the resources needed by the task, If we don't specify it, it's 0.
Uh,
Because if you have like 5 kind of resources, we will be forced to define for each task, each resources.
a good question. I don't think that's possible. I should ask. So the scheduling library, the scheduling part is defined by Guillaume, with me. So I think that I should ask him. I think it's not possible to do this.
So
You have to define all the resource consumption, even if it's 0.
okay, so for task 1, if there are 3 resources, I must specify L1 0, L2 1, L3 0, for instance.
Yeah, for each resource.
For each task, okay.
Yeah.
Right.
Yes.
It's a task of scripting a bit of combination. So.
Yeah, but okay. If you do it with a for loop or something like that, it's quite rapid, I would say, to do that. Also, in practice, we often use the PSPlib format, which is a well-known format for RCPSPs that we directly read. We directly parse it and create this class. So, meaning that here we show you, for the purpose of the demonstration, how to do it by hand. But a common practice is more to define the PSPlib format and then to parse it in scikit-decide directly. Okay, and finally, we have the maximum capacity of the resource here, which is, in that case, 7. All right. Now, once you've defined a very simple RCPSP domain, we will create it. So set in place environment, so it's a detail. So there is a way in scikit-decide when you want to solve the scaling problems with reinforcement learning, to modify the problem in place or not. Too much detail. So here we don't want to do it. So it's why we set it to false. To show you how we can model, how we can cast this scaling problem into reinforcement learning one or planning one, we get the initial state of the domain. So the library, when you do that, automatically cast it to a planning problem, and then allows you to call planning functions, basically. And let's see what we have. So the state is quite complex when you want to represent scaling problems like that. It contains everything that we told before, that we said before, sorry. And it's a lot. Huh? You have the resource task consumption, for instance, the task IDs, the tasks that have been completed, and so on. So it's a huge dictionary, and this is why it's not very efficient to solve scaling problems like that. What are the applicable actions in the initial state when you begin with an empty schedule? You can do only 2 things, either starting the task 1, which has only 1 mode in this case. The action type is to start it. There is no progress yet, and no resource consumed so far. Or you can do nothing and let the time progress. So to solve our CPSP domains, we'll study 3 different ways. So calling graph search algorithm with a casted domain, or using combinatorial optimization and heuristics, which is obviously the state of the art, and you can scale with this kind of algorithm. Or why not reinforcement learning? So let's try with A star. So it's very quick in that case because the problem is small, but pay attention that the size of the problem exponentially grows with the number of tasks and resources. So it's very small here because the problem is tiny. If you increase the number of tasks, even with 10 tasks, it's totally intractable with A star. Okay. So let's plot the result. We only have 3 tasks here, and so yeah, we can check that it's optimal, it's obvious, and this task can be only executed after that one, and that one can be done in parallel. So we have this. We also have the representation of the task, the resource consumption, sorry. So for each resource, you would, the library, we would plot here a different graph per resource. Since we only have 1 resource, we have only 1 plot here. So the red line is the maximum consumed resource. If you have different tasks consuming it, they would be on top of each other. and you check that you never exceed the dash line. Yeah. So if your algorithm is bugged or does not respect the constraints, then you would exceed this dash line. Okay, but we already said that we cannot scale with this. It's impossible because the program exponentially grows with a number of states. So to do this, we rather use constraint programming or mixed integer programming or meta-heuristics algorithms.
So why are you referring to A-star and ICAPS? Maybe this is not important. It's just that you basically what I'm asking is in A-star you have the ability to define a heuristic function for A-star.
You could do this, but for scheduling, it's not easy to come with a good heuristics. So, in fact, we did that because we thought that we could come to new ideas by allowing a given domain from a given community to be solved by algorithms from another community. We could imagine new heuristics to solve scaling problems, for instance, with A-star, this kind of stuff. And in fact, it also allows us to solve scaling problems with reinforcement learning. It's at the end of this notebook. And you will see that it works this time much better than A-star. You can learn, in fact, generic policies for scheduling. So in this notebook, we will limit ourselves to fixed size scheduling problems, but what we have done, and we had a paper last year at ICAPS, is to learn to solve scheduling problems with graph neural networks by doing the same, in fact, exactly the same cast. And this time it works well, and you can generalize. Okay, I can come back to it at the end of the notebook. But let's come back to the state of the art, which is combinatorial optimization. So we rely on another library, which is discrete optimization, also developed by Airbus, which is a general library to solve any kind of combinatorial optimization problems, mostly from the deterministic world. So discrete optimization problems, let's say. So besides scheduling, it allows you to solve many kinds of problems from knapsack, coloring, TSP, VRP, maximum independent set, a lot of things. So even if it's not the topic today, I encourage you to have a look at this library, which is extremely complete also. It provides algorithms from mathematical programming methods, local search and genetic algorithms, and custom heuristics. So for some problems, there are very good heuristics that work well. For instance, for queue scheduling, which are also provided by the library. So let's import now a specific domain instance from the library. So in the RCPSP community, one format which is well known is a SM format. And so from discrete optimization, you can import a lot of those domains here. And we will specifically load that one, which is quite challenging. It has already 120 tasks, so much beyond the capacity of I-star. And you will see that it's extremely easy to be solved with constraint programming. So the first thing we do is that import the CPSAT solver from discrete optimization, which is a bridge to the OR tool CPSAT solver, in fact. So you don't have to model your problem in CPSAT. It's already done by the library. And so from scikit-decide point of view, it comes to import the DO solver, DO for discrete optimization solver, which is a bridge to the discrete optimization library. And the only thing you have to do is to say that your domain factory will create a RCPSP domain, that the solving method is constraint programming, CP, if minizing is available. Else, it will use a default solver, which is, I think, the default solver will be Shift. Yeah. If minizing is not available, it will use Shift. Okay. Let's do this. You call solve. So in fact, it took time mainly to import the library and and compile the third Python script. The solve function is very quick. I know you can roll out it using scikit-decide. It's interesting because when you solve constraint programming problem with CPSAT, it just gives you the starting time of the task and so on. But if you re-import the solution in scikit-decide, you can again roll out it by constricting, those intermediate state and actions from the planning point of view. Even if it was solved using constraint programming. And so now we plot it to have a nice view of the schedule. So no need to comment the plotting script. We are just interested in the result. So again, what takes time here is to create the visualization, because you saw that solving it was very quick. So what it's doing here is creating, so it's generating many different images and then merging all of them in a GIF file. And it is what's taking time here. Oh, okay, here it is.
Is it generating on the go, or is it already the GIF here?
It has been generated just now.
Okay, so
by me.
generating. Is it just an animation?
It's an animation here.
Oh, okay.
Yes, but here I have regenerated it. And normally, if you execute the cell, you should get the same animation as I'm obtaining here. Okay, so we see that this problem is much more complex, and you saw it was solved in a couple of seconds, even less. Okay, so one thing, and we spoke about it before, is to know the best parameters. You have plenty different choices of algorithms. You can use constraint programming. You can use meta heuristics. You can use, I don't know, MILP, mixed integer linear programming. Each of them have different parameters. And so it's important to know what is the best algorithm. Is there a way to quickly compare all those algorithms? So it has been implemented in discrete optimization. This is what we are now porting to the whole library, as I told you. Yeah. So for discrete optimization, we will try to compare all those algorithms, so large neighborhood search, which is, by the way, the thing that works the best for our Airbus internal problems, where we have thousands of tasks and not 120. So it's just a remark. So if you have a very complex problem to solve, I advise you to try large neighborhood search from the library. We have the RCPSP solver. We have the CP solver for CPSP coming from Minizyme. We have genetic algorithm solvers, and so on. So many different things. And so we want to compare all of them. What is the space of options, of possibilities? So for CP solver, we have a lot of hyperparameters. So the algorithms that can be used, and for Shift, for instance, so sorry, you can use Shift, you can use G-code, which is or Cplex or CPOpt, all of those. Gurobi if you have a license, and so on. For LNS, so large neighborhood search and consists in freezing some variables, optimizing the problem when you freeze those variables, and then randomly choosing other variables, freezing them again, and so on. So it means that it relies somehow on a constraint programming solver. And again, you have different choices here. Well, you see the same for local search, for genetic algorithms, and so on. And so to compare them, we will use Optuna. Optuna is a famous framework to benchmark different options that is used extensively in reinforcement learning. And so that we port it to constraint programming and scheduling problems. So that's one. I think I won't run it because it takes really a lot of time. You've seen all the different options. So it won't take 1 hour, but several minutes. So I won't run it. I will import the solutions that we have already run on our side. So this cell will import the solution and normally load the Optina window here. Okay. So when you've done this, you can compare different things. So each point here is a different algorithm with a different parameter. And the red line for each problem, so in the, we have the different trials that we've done. And for each trial, we have the best algorithm each time, and that's the red line here. Okay. For the max span, which is the duration of the schedule, it can be also the elapsed time, so running time of the solver, and this is very sparse here. What's interesting, I think you can go here. Yeah, you have the view per trial, and for each trial, you have the name of the algorithm that was tried. Here is genetic algorithm. Here is handmade heuristic, pile solver from the literature, and so on. There is one view where we can see all of them, which is nice. Searching for it.
I think the second page is the right one if you want to try this. Stay here, just go up. And the second icon, the one with the lens, analytics.
Yes.
And you can go down and there's something, I don't know what it is, but there is something. Let's just go down.
Yes, I was searching for that one. Thank you. Yeah, so here it's a different view indeed. But no, it was not, sorry, that one. I'm a bit lost with this Optina window. There is a view where you see all the different runs in parallel. Where is it? Maybe. Yeah, I think it was here. Yes, okay, that one. So here you see per algorithmic step, because most of those algorithms are anytime, so they improve over time. And here we want to minimize the cost and the max span, which comes to maximizing the negative reward somehow. Okay, this is why you see here increasing here, but all those numbers are negative. And so you can directly compare all the algorithms and see how they improve over time. It's important because if you only have 10 minutes to optimize your problem, you want to know after 10 minutes what is the best one, how they behave over time. And so this view is quite practical. And so in that case, we see that clearly those two algorithms here would be the best. Yeah, because those are the ones that improve the fastest in a very few times for this problem. Okay, and so what is the lesson here? Is that to compare the different algorithms, it's very easy with the library. It's only, this cell, this line of code. You define your hyperparams from here. And once you've defined them, you just call run Optina multisolve. And you take several coffee, you wait. Yeah, now it's time for coffee, but when you run it, it takes a lot of time. So you come back 1 hour later and see the results of all your algorithms.
Sorry, what you're saying is that we should run it during the break?
If you want, you can try. I don't know how much time it takes. Maybe one hour or so. But it won't you bring much at what we already saw, because what I just saw is I loaded the result of this computation.
For the reinforcement learning one, I missed this.
No, for the hyperparameter.
Oh, I see. But we haven't discussed reinforcement learning.
No.
I see. Okay.
That's it. Okay, so now what I propose to take the break. We'll see how to solve RCPSP with reinforcement learning, and after we'll look at PDDL solving and how to create domain and solvers, and we'll be done. Okay?
Great. Thank you.